thank you all for coming. There are 25 people here tonight, actually 26, somebody just showed up. Of course, that includes myself and Judy. And why are 25 people taking an hour and a quarter or however long out of their day on a Sunday, on a summer evening to listen to this? And the reason you are here, and the reason you're spending your time doing this, is because aliens are cool. Everybody's really interested in the concept of aliens, and it's kind of been a thing for approximately 500 years, ever since Copernicus knocked us out of the center of the universe. Because once Copernicus knocked us out of the center of the universe, that kind of opened up the floor for people who were not us. So to demonstrate the fact that people have been interested in aliens for quite a long time, what I want to do first is just very quickly kind of step backwards through alien memory lane, just to reinforce the point that the whole topic is something that tends to grab people's attention and has been doing so for a very long time. By the way, this image here, this bizarre image, is a tourist display at Roswell, New Mexico, you know, where the UFO supposedly crashed, and you get to lie on the table and get your very own alien probe. Anyway, so let's step back. We think that they may be out there. We believe that because life is tenacious, because the universe is a very big place. And there's a lot of buts associated with that. And if they are out there, we have no idea how advanced life may be. But the one thing we know for certain is that we're very interested in the topic. And as I said, have been interested for hundreds of years. So let me step back a little bit. Actually, I'm getting ahead of myself. This is a galaxy that looks very much like our own. This is the Andromeda Galaxy. It's about 2 million light years away from our own galaxy, 1.5 million. It is a very large galaxy. It is comparable in size to our own, maybe somewhat bigger than our own. And it has about 1 trillion stars. That's the one followed by 12 zeros. Our own Milky Way is comparable in size, maybe about half that size, 300 to 500 billion stars. So a huge number. And on top of the fact that we have on the order of 500 million stars in our own galaxy, there are approximately 100 billion galaxies in the observable universe. So that's, if you multiply those two numbers together, you get a huge number of stars that potentially are candidates for having planets with life. And just to try and place that in perspective, I offer you here in this image what's called the Hubble Deep Field. This image was actually taken, I think about 15 years ago by the Hubble Space Telescope. And it's quite a striking image, because if you look at it carefully, what you will see is that a very large fraction of the blobs in this image are not stars, but galaxies. So for example, this guy in the center here, and all these little oddly shaped things here throughout, these are all entire galaxies. They are not individual stars. So when you see this picture, you know you're looking at a vast amount of space and a vast amount of matter and a vast amount of everything. And it's fair to ask, well, what fraction of the universe are we looking at when we look at this remarkable picture taken by Hubble? And so I am going to tell you how big a piece of the sky this is. If you hold a sewing needle at arm's length, this is what it looks like. So in other words, the area of the sky in this picture is comparable to the area that you see through the hole in the sewing needle held at arm's length. In other words, this is a truly microscopic piece of the sky that you're looking at here, and yet everything you see in it is galaxies, which is another way of saying that the universe is just an astonishingly vast place and consequently carries many, many, many opportunities to create life. To give you another sense of perspective on that, here's a picture of a beach. If you add up, if you're extremely patient, and you start counting now, and you start counting all the grains of sand in all the beaches of the world, down to a depth of I don't know, 30 or 50 feet or so, you will count, and there is no name for this number, but in this case, the number of grains of sand is very roughly speaking 1 followed by 21 zeros. It is believed that the number of stars in the observable universe is somewhere between that number and about 10 times that number. In other words, the number of stars in the observable universe is 1 followed by 21 or 22 zeros, which is greater than the number of grains of sand in all of the beaches of the world. So keep that in perspective. And to make it even worse, to bend your mind a little bit, if it were to scale, if the sun were to be reduced to the size of a grain of sand, then the nearest star, which is to say the nearest next grain of sand, would be 3 miles away. So it's mostly empty, but there's a lot of stuff in the empty. So that gives our imagination plenty of elbow room. And as I said earlier, when I was getting ahead of myself, that imagination has been running rampant for literally centuries. So let's take a little step back in time through the popular imagination. 2016, it's a nice movie, 6 years ago, Arrival, if you happen to see it. The aliens in that movie looked like octopuses, only they had 7 legs, and they were very strange and very alien, and it was a very interesting movie. Let's keep marching back in time. All right, in 2009, and then finally this summer, the sequel, 13 years later, Avatar, right? Very handsome blue people who were, fighting off, exploitive white guys mostly, but nonetheless alien. Stepping back further, 1996, Independence Day. These guys got defeated by Jeff Goldblum when he inserted a virus into their computer. Seems astonishingly unlikely, but this is what those aliens look like. 1996. Let's keep stepping back. 1982, everybody's most cuddly alien, E.T. I don't think I need to say anything more about that. He ate Reese's Pieces and he flew across the moon, and everybody knows this. Continuing further back, 1979, Alien, very scary, and all the sequels as well. 1968, Space Odyssey. You never even got to see the aliens, but they made themselves known through the monolith, and then the apes got all intelligent and all sorts of things happened and nobody understood the ending. But it was a really classic movie, and they were certainly very alien aliens. So now we're back to 1968. We've gone back 44 years already, 54 years. 1964, you know who this is. Star Trek was first broadcast in that year, and Mr. Spock, of course, immediately became a cultural icon that resonates to this very day. Going further back, wait, we have a message in chat. E.T. was just on this weekend. I still cry at the end. Right. Yes, there are no spoilers for the movies here. Continuing back in time. 1951. If you claim you like science fiction, there is a gap in your education if you have not seen this movie. The Day the Earth Stood Still. A very classic, one of the very greatest science fiction movies of all time. That's actually the alien on the right, played by Michael Rennie. That's his bodyguard robot in the background. Since everybody in the chat today, in the talk today is old, you probably remember the phrase Klaatu Barada Nikto, and this is where it comes from. But we can go further back still. 1948, Flash Gordon. They knew how to make aliens in 1948. It was very important to have a Fu Manchu mustache and beard. That, of course, is Ming the Merciless on the right. Going back further still, 1897, The War of the Worlds by H.G. Wells was later made into it's made into a movie several times. In 1953, I don't know, at least 2 or 3 times that I can think of. And of course, as you doubtless all know, these particular aliens were from Mars and they were felled by terrestrial bacteria. 1835, now we're probably getting into an era where you're a little bit less familiar. In 1835, the New York Sun newspaper decided to goose its circulation numbers by running a blockbuster expose about life on the moon. And they quoted a very well-known English astronomer of the day, a guy named John Herschel, who was a real honest-to-God astronomer, quite an accomplished one, in fact. And the New York Sun quoted John Herschel as saying, as saying that he had discovered a civilization on the moon, and people flew around with angel wings, and it was a really wonderful place, and all sorts of people got excited about this. They ran it as a 6-part series in New York City in 1835. John Herschel himself was quite amused by this for a little while until the fan mail started flooding in, and he got sick and tired of the whole thing. But this was not the first of this sort of thing. We can go all the way back to 1608. Johann Kepler, whose laws of planetary motion are still in use today by NASA for their calculations, wrote what is considered the first science fiction novel. It was called Somnium. And in this particular novel, a man, when he falls asleep in his dream world, he travels to other planets. 1608, that's pretty far back. 414 years. And we can't go much further back than that as far as imagining aliens, because by the time you get 50 or 100 years earlier than that, you're getting into the pre-Copernican era, when everybody thought that the Earth was the center of the universe and there was no reason to think about people or aliens anywhere else because we were all there was except for God. And so it is for this reason that this particular work from 1608 is reasonably considered to be the first science fiction novel and the first appearance of aliens in what you could consider to be the popular culture. And that's all well and good. And of course, it leads to the obvious question is that if there are aliens out there or life in any form, what might they look like and how could they arise? And now we'll get into some actual science after a little bit more popular culture. They could be humanoid, and of course these are ones that you're all familiar with. We just looked at them, and of course they all look rather like people in one form or another. Even the alien from the Alien movies, you know, that Sigourney Weaver kept blowing up, look kind of humanoid in the sense of having 2 arms, 2 legs, a face, and so forth. And the reason for that is pretty clear, right? It's easy to imagine someone or something that looks like yourself. And if you're budgeting a Hollywood movie, it's a lot easier to make a costume for an actual person than it is to build, you know, something completely strange looking. But people do that. We have imaginations and creativity. And so when people think about aliens, their first thought may go to some humanoid life form, but not always and not necessarily. So here's some very non-human ones. So on the upper left there, we have a Star Trek episode with an alien based on silicon instead of carbon who went around burrowing through rock walls. On the upper right, we have a really strange alien from a Tom Cruise movie called Edge of Tomorrow, which I recommend very highly. In the lower left, we have the sandworms from Dune. And in the lower right, we have the Blob. I forget what year that movie was made. It was in the 50s, and it was one of Steve McQueen's first movie. He was only about 20 years old or so, and he and a bunch of other teenagers driving hot rods managed to defeat the Blob. So these particular aliens have the virtue, if you call it such, of at least not being constrained to be humanoid in appearance. And that's a pretty reasonable point of view, because no matter where alien life arises, form must follow function. Just as on our planet, environmental factors drive evolution, and evolution drives appearance. That's what form follows function means. It's why fish are very aerodynamic, it's why birds are very light, and so on and so forth. And so whatever extraterrestrial life is going to look like, it is going to be determined primarily by the local environment, whatever it may be. We have an alien environment in our own world, which is, of course, the oceans. And the oceans are indeed very alien to us. They have been only about a third explored. Some people use a much smaller number than that. I've seen numbers as low as 5%. Only 20% of the seafloor has been mapped. It is estimated that 90% of the marine species have yet to be discovered. And so we can pretty safely assume that when you get to these very large unexplored parts of the ocean, we're going to see morphologies and even biology, particularly at the greatest depths, that is very alien to us in the deepest sense of the word. So we have an alien world right here on our own planet, and it's very tough to explore, right? Because it's hard to get to the bottom of the ocean. But we know that life is there. We know that it takes many forms, and we know that some of those forms are very different from what we're used to. For example, at the very greatest depths, there are volcanic vents, undersea vents. It was thought before these were discovered that it was not possible to have life at these greatest depths because there is no sunlight. And it was long thought that you needed sunlight as an energy source to power biology. That turns out not to be true, because these undersea vents are volcanic, they are hot, They give out a lot of sulfur and sulfur compounds. And sulfur has a lot of chemical similarities to oxygen. And so a lot of the biological and metabolic processes that take place on land can take place in the deepest oceans without any sunlight at all by using these sulfurous volcanic vents as an energy source. And until these were discovered, which is only a few decades ago, it was believed that nothing like this could exist. And yet here they are, right? We have worms, we've got a crab, you can see clams here, and these are existing at depths down at 10 and 20,000 feet in the ocean, where it was previously thought there could be little or no life because there's no sunlight, there's no heat, there's no anything, and yet life thrives even there. This formidable looking creature looks like the world's weirdest plush toy. It is in fact called a tardigrade. Its technical, well, not entirely technical, its popular name, I suppose, is a water bear. And the reason it looks kind of odd looking, besides its shape itself in this picture, is that this picture was taken with an electron microscope. This guy is about 0.5 millimeter long, very, very tiny. But the reason the tardigrades are important, even at their tiny size, is that they are basically indestructible. Tardigrades can survive anywhere. Tardigrades can live on space missions. They can live in any environment on Earth. They can survive an extraordinary range of temperatures, pressures, and so forth that would kill just about any other life form. For example, some types of tardigrades can withstand cold down to 450 degrees below 0 Fahrenheit. They can withstand heat greater than boiling water. They can withstand atmospheric pressures of 1,000 times surface atmosphere, and they can go without food or water for 30 years. Tardigrades are the most resilient animal known to science, and it is for this reason that this type of creature is called an extremophile, because it likes extreme environments and can survive there. And it is the fact that creatures like this exist that tells us that there is cause for optimism for finding life in some form outside of Earth, because things may be really tough in the environments outside of Earth, but we already know that we've got a creature here that can survive really tough environments. Now, that's a two-edged sword. Life is extremely tenacious, right? There's a wide range of life under hostile conditions, which, as I just said, increases the chances of finding it elsewhere, but it also increases the chances that when we do find life somewhere else, we brought it there by mistake. This is a very big concern for the Mars missions, because things like tardigrades and certain bacteria can survive the trip through space. And the last thing you want to do is seed another planet with our own life forms. And it is for this reason that NASA has the incredibly cool Office of Planetary Protection. Wouldn't you like to work in an office that had a name like this? What do you do? I work in the Office of Planetary Protection. Well, you can read the bullets here to see what that office does. Preserving our ability to study other worlds as they exist in their natural states, avoiding the biological contamination of explored environments, and ensuring that we take prudent precautions to protect Earth's biosphere in case life does exist elsewhere. These guys take their job seriously. These guys put all space missions, all planetary space missions, through an astonishing array of decontamination measures to make sure that when our space probes arrive in other places, they are not bringing some passengers along from Earth. So this is a real thing. There's a chat. Give me just a second. Yes, the prime directive from Star Trek, right? Don't interfere. So the obvious questions that arise, given the fact that life seems so very tenacious, how and where can we find it? How advanced is it? Is it something as basic as single cell microbes? Is it likely to be found in a more evolved state? Plants or even animals? If it's animals, could it even be intelligent? And if it's intelligent, how would we communicate with it? These are all questions that, people at NASA actually worry about. And one of the first people to worry about it was this guy, Frank Drake, who is still hale and hearty, at least I hope he is, at the age of 92. He was actually my first radio astronomy professor 50 years ago. Wow. And he is actually well known for many things in astronomy, but the thing he is most well known for is the equation that is written on the whiteboard behind him, which is called the Drake equation. And what it does is it relates, and I'm not going to go through it in detail because that's kind of beyond the scope of this talk, but the two important variables here are the N on the left and the L on the right. And what the N is the number of intelligent civilizations in the galaxy. And what the L is the lifetime of such civilizations. So Drake took the audacious move of trying to calculate how many, not just how much life there was in the galaxy, but how many intelligent civilizations existed in the galaxy. And it turns out there's a kind of a rough sort of philosophically quantitative way to do that. It's embodied in this equation. And it turns out that when you plug in assorted factors and things, it can be reduced to a very simple form, which I will show you in a second. Drake actually tried to put this to the test when he was a graduate student. And he used one of the major radio telescopes at the time, which was located in Green Bank, West Virginia. And he searched a little part of the sky for what might reasonably be interpreted as intelligent radio signals from outer space. He did not find any. It was called Project Ozma, who was the queen in The Wizard of Oz, you might recall if you ever read the books. He did this in 1960, so I guess he was a postdoc. He was 30 years old. And needless to say, he didn't find anything. But this was a breakthrough effort. No one had ever tried to actually look for intelligent life in the universe before, and Drake did that. So that equation, again, has all this stuff in it. It's got asterisks, it's got subscripts, and it's all very intimidating looking. But it turns out that when you do some analysis, it boils down to something very simple. And it is this equation, which is considered the simplest form of the Drake equation. And it says a very simple thing, N equals L. You don't have to know a lot of math to know that that's just one thing equaling another. And what this is, as I said before, N is the number of extrasolar civilizations in the galaxy, and L is the average lifetime of a civilization. In other words, if civilizations arise and fall throughout the galaxy, and if the average civilization lasts 1,000 years, then we expect to find 1,000 of them in the galaxy. That sounds like a lot, but the galaxy is a really big place, and they're likely to be far apart. But nonetheless, what this equation tells us, very optimistically, is that if intelligent civilizations do arise, and if they last for a very long time, in other words, if L is a big number, then N is a big number. So if civilizations last for a long time, then this equation implies that there are a lot of them throughout the galaxy, which increases our odds of finding one. But there's an issue. What do we mean by the word lifetime? Human civilization, at least recorded history, is about 5,000 years old. And you can say, well, okay, well, if civilizations last 5,000 years, then we could expect 5,000 of them to be found throughout the galaxy. But think about a 5,000-year-old civilization. Think about the earliest pharaonic dynasties in Egypt. Would we be able to communicate with them? Certainly, we don't have any technology in common. Or imagine a civilization that's 5,000 years or even 1,000 years ahead of us. If they were sending us a signal, would we recognize it? If we could somehow communicate with ancient Egyptians and we broadcast radio signals to them, it wouldn't do the slightest bit of good because, of course, ancient Egyptians did not have radio and they wouldn't know how to receive it. And so that kind of narrows the field some. In fact, Carl Sagan used to say that as a way of illustrating the problem, that if you had some pre-technological civilization in some unexplored part of Africa that communicated from one village to another entirely by drums, and you asked them, how would you communicate with a distant village, a distant civilization? They'd say, oh, we'd build a really big drum. And that's the problem, because once you go past a certain age or a certain degree of technological sophistication, you're not using drums anymore. Or maybe you're not using radio, or maybe you're not using anything that we currently have today. And so consequently, you have to temper your expectations, because when we talk about the lifetime of a civilization, what we really mean from practical purposes is the length of time over which we can communicate with some common technology. In other words, the real lifetime of the ability to communicate for a civilization is how long its communications technology stays relevant. Consider our own technology. I mean, look how much mobile phones have changed, in the last 10 or 20 years, gotten so much more sophisticated. They operate at different wavelengths than they used to. They're digital now. They used to be analog. Technology changes very rapidly. And we can only search the heavens, we can only communicate with anybody we find with the technology that we have. And that kind of boxes us in some. So consequently, the effective length of a civilization may be a relatively short period of time. And in fact, based on some research that I did, we determined that if that length of time is less than 1,500 years, in other words, if there are fewer than 1,500 civilizations throughout the galaxy, then on average, we're too far apart, because we won't be around. If we send out a message, we won't be around long enough to receive the answer, or at least won't be around long enough to understand the answer if we receive it, because our technology will be too out of date. So that's a little bit of a problem. In fact, it's a big problem. So we try anyway. All right, so fine, we can't communicate by radio. How can we communicate? Well, we could actually send a package, and we actually did this. This is a gold, let's see, I think the plate is made of titanium and it's coated in gold. And this is a plate that was etched with some important important information about our civilization, was attached to an interstellar space probe, not as part of its primary payload, but just because we could. And then it was launched. This is called the Pioneer plaque, and it tells something about us. I think I have a slide, right? So this thing in the background is actually kind of a schematic of the Pioneer spacecraft compared to the size of a man and a woman. This is a hydrogen atom. Hydrogen has a radio emission at a certain wavelength, and so that's what this thing over here is. It tells how tall these people are in wavelengths. This is a map of a certain type of neutron star that locates us in the galaxy. And here's a little picture of our solar system with a Pioneer spacecraft heading outward bound. This was launched, I believe, in 1972. It has now left the solar system, and on interstellar scales, it hasn't gotten anywhere yet. But the point is, it's kind of a philosophical exercise, right? We are reaching out to the beyond. Yes, 1972. It was actually, the primary mission was to go to Jupiter, which it did. But having taken pictures and made measurements of Jupiter, it used Jupiter's gravity as a slingshot, and then shot itself out of the solar system. Now it's way beyond the orbit of Pluto. Another probe in which we did something similar. And here's a picture of Jupiter from Pioneer 10. And that is one of Jupiter's moons transiting across the front. Pioneer 10, as I said, used Jupiter's gravity to slingshot out of the solar system. Two subsequent missions, Voyager 1 and Voyager 2, did the same thing, and they are also exiting the solar system. The two Voyager probes also carried a message to potential aliens who might happen to be in the neighborhood and pick it up. There's the Voyager spacecraft. And there is a picture of Saturn and 3 of its moons taken by the Voyager spacecraft on its way out of the solar system. Quite spectacular pictures. And this is what Voyager carried. It's not a plaque, although it has some of the same information on it. It is a record. It's basically a DVD etched in gold. And it has a huge amount of information on it, which hopefully some very smart alien would figure out how to decode. And it has lots of sounds. They recorded samples of a large fraction of human languages, all different kinds of music, birds chirping, just everything, just lots and lots of information about our planet etched into this gold record. And it's about a size, remember the old laser discs from about 30, 40 years ago? It's about that size, it's about a foot across. And it tells a lot about Earth to anybody who happens to retrieve it, the odds of which are vanishingly small, which did not prevent the writers of Star Trek from hypothesizing that somebody found it and reconfigured the spacecraft and sent it back to Earth, and actually made life miserable for everybody until they figured out how to destroy it. So that's actually a bit of the Voyager spacecraft model of it in the background there, with Captain Kirk and Mr. Spock all looking very concerned for good reason. But the first real message that could in principle be received by someone with somewhat better odds than a metal plate at the edge of the solar system was broadcast from here. This is the Arecibo Observatory, or I should say, rather sadly, this was the Arecibo Observatory. Unfortunately, there was a terrible disaster last year. This observatory was built in the mid-60s, For decades, it was the largest radio telescope in the world. Is located in Puerto Rico. It is where I cut my teeth as an astronomer and did my very first research. And to give you an idea of the scale, from one end of the dish to the other is 1,000 feet. This thing at the top here is about 300 feet across. It's suspended 600 feet above it. And it not only receives very faint radio signals, but it can also transmit. They use it to bounce radio signals off of planets and asteroids. And unfortunately, this is what it looks like today. After 50 years of operation, this cable snapped and the whole thing collapsed. I have actually been up there many, many times. And now, unfortunately, it is no more, and it's very sad. So this happened about 1.5 years ago. Nonetheless, in its day, as I mentioned, it was the largest radio telescope in the world, 1,000 feet across, made out of aluminum panels that are polished to an accuracy of 1/8 of an inch, 14 acres of aluminum panels, and has a radar transmitter, can transmit a very tight beam at 1 megawatt, so a very, very powerful transmitter. But that's all well and good, but what do you know how to transmit? How can you transmit something that, if it is received by some distant intelligence, could be comprehensibly understood? Well, first you get together a bunch of graduate students, and that's me in the center at the age of 21. And I would kill to have hair like that today, but it's long gone. Both of my graduate student colleagues there are both at NASA today. The guy on the left is a Randy Kimball. He became a senior person on the Hubble Space Telescope. And the guy on the right is Phúc Quoc Lee, who is at the Jet Propulsion Laboratory, and he was in charge of certain small satellite programs. So we all managed to live our professional lives after this picture was taken way too long ago. And led by some people who were rather more senior and smarter than us, guys like Frank Drake himself and Carl Sagan, we created a message, which we broadcast as a binary code. And this is what the message looked like. You got a picture of a person in the center here. I'm not going to go through the whole thing because there's actually a lot of information here, but there's a person, there's the height of the person, this is the number of people, there's a little model of the solar system underneath the people there. This is the Arecibo dish itself. These are basically chemical representations of amino acids in the DNA. And this kind of swirly thing here is a model of a DNA molecule. So there's actually quite a bit of information here, and the number of bits in this message is 1,679. Why such a strange number? And the answer is that it is the product of two prime numbers, 23 and 73. So if you were to receive this string of bits all in a row, you lay them out in front of you and say 1,679 bits, and some are on and some are off, which is to say some are black and some are white, some are ones or some are zeros, however you choose to interpret it. What am I supposed to do with 1,679 bits? And the answer is there's two ways you can arrange it into a rectangle, either 23 rows by 73 columns or 23 columns by 73 rows. And if you do the latter, 23 columns by 73 rows, you get this nice picture. And if you do it the other way, with 23 rows and 73 columns, it looks like gibberish. And so by using this clever technique of multiplying prime numbers, you can actually create a little raster message here, and that is what we did. And so this message was broadcast in 1974. It was really kind of a symbolic exercise. And this is where we aimed it. We aimed it to a collection of 300,000 stars located 50,000 light years away. And the reason we chose that particular target is because this particular cluster of stars happens to be about the same size as the beam from the transmission itself. And so by sending out these 1,679 bits, you manage to blanket 300,000 stars and hope that somebody there is listening, which is highly unlikely. But again, it's a symbolic measure. I mean, in a way, it's a message to ourselves just to show that we can do it. But of course, the other problem is that it's 50,000 light years away. So by the time we get a reply, nobody is home, because that takes 100,000 years. And that is one of the reasons that we know that the effort was purely symbolic. But it does raise a question. If life is plentiful and it is not uncommon for technology to be developed, then presumably somebody is smarter than us. In fact, lots of somebodies are smarter than us. You can assume that we're average, may not be a good assumption, but what else have we got? And if we're average, that means there's a lot of people smarter than us. And if there's a lot of people smarter than us, then why haven't they colonized the galaxy yet? Or at least why haven't we seen any evidence of that? This problem was originally posed by Enrico Fermi, the guy who first made nuclear fission happen, and is called the Fermi paradox. If nothing about our planet is special, someone should have colonized the galaxy by now, and we should be surrounded by civilizations, extraterrestrial civilizations. We don't see it. Where are they? Well, that assumption of mediocrity has three pretty innocuous things behind it. We're not special. Life could arise elsewhere, just as it has on Earth. We are likely neither the first nor the last planet to support intelligent life. And the safest of the three assumptions is that the same laws of physics and statistics apply everywhere. And there's good reasons to believe that last one. So if we're not special and everybody's got the same physics, and well, where are they? Nobody knows. There's a couple of possibilities. One is that there isn't anyone elsewhere. That of those trillions and trillions of stars, we are the only planet with intelligent life. It's possible. It's pretty depressing, but it's possible. Another possibility is that civilizations are common, that they're out there, but colonizing the galaxy and achieving interstellar flight is just too hard. And so nobody's done it. Technological difficulties, it may be just too hard to get people to do it, or it may be that when you get really smart, you blow yourself up, which, we certainly seem inclined to do. And the third possibility is that it did happen and that they're here and we don't see them because they're watching us or we can't detect them or they don't want us to know that they're there. Who knows? It's kind of a paranoid way of looking at it, but there's no evidence against it. The problem, of course, is that we've only got one data point, and that is our planet. And so in order to have an idea of how to resolve the Fermi paradox, and whether or not there is life elsewhere, we need more data, which is another way of saying we need more planets to look at. So the first place to look, if you're looking for life somewhere and you need more planets, well, we have some nearby, right? And we've started exploring them because we have a perfectly good solar system here with some really nice planets in it. And none of them seem quite as homey as Earth does, but that doesn't mean that they can't support life. So what does it take? What does it take to support life? Well, we think you need carbon, because every living thing we know of uses it, but we don't know, it's not certain. Every living thing we know of has potassium in it, and a couple other elements as well. We know that you need energy of some sort because it's got to replicate in order to evolve. And as far as we can tell, you need water. So those are kind of the big five, right? Carbon, potassium, a couple other elements, an energy source, and water. Those are the bare necessities that we believe you need to have life. And that's not a horribly demanding list. The interesting thing is that if you look around carefully, you can find a lot of the building blocks. For example, we're made out of, well, we're not made out of DNA, but we're sort of encoded by DNA. And DNA replicates itself using RNA, ribonucleic acid. And RNA is made out of 4 amino acids called uracil, cytosine, adenine, and guanine. And if you got a fifth one called thymine, then you can make DNA. Well, okay, well, those are very complicated looking chemicals here, but guess what? We have found them. We have found all 5 of those amino acids and 15 others on asteroids. And in fact, very recently, this is an asteroid on the left here, it's called Ryugu. There was a Japanese sample return probe to it called Hayabusa, which only very recently, in the last few months, I think, maybe a year ago, brought back 5 grams of dirt from this asteroid. The asteroid's about 1 kilometer across, and the probe actually landed on it and scooped up a little bit of stuff and came back. And they analyzed it, and lo and behold, they find 20 different amino acids on this asteroid. Amino acids have also been found in meteorites that have fallen to Earth. You see them shooting star across the sky, it falls to Earth. Sometimes they find the rock, and they drill inside the rock, and they can find amino acids in there. This is really profound, because if you're finding amino acids on places like asteroids and in meteorites, then the implication is that those basic building blocks, those chemical building blocks for life, may have originated in space, because we know it's there. We already know that there are complicated organic compounds that are found in clouds of gas throughout the universe. There is a huge cloud of alcohol near the center of the galaxy. Party time, trillions of gallons in gaseous form. So the implication is that life on a planet can be seeded from space because the building blocks are already there, literally floating around. And so the implication is that life may be plentiful throughout the galaxy. Another implication is that life on Earth may have originated because of having been seeded by these building blocks from space. We still have the issue of water. Amino acids by themselves are not going to do the job. This stuff is really important. Water, water everywhere. And in order to have water, particularly liquid water, you'd like your planet to be in what's actually called the Goldilocks zone, or more technically, the habitable zone, where liquid water can exist. In our own solar system, Mercury is very close to the sun, too hot. Pluto and Uranus and Neptune, too far from the sun, too cold, can't have liquid water. But these guys, Venus, Earth, Mars, those are in a region at a distance from the sun that, in principle, were their environment to allow it, temperature would allow the existence of liquid water. And so when we're searching for planets outside of our own solar system, one of the things we're very interested in is finding planets that might live in that Goldilocks zone, because those are the guys that might have liquid water and consequently could, at least in principle, support life as we know it. You all know about the Mars rovers. There's a whole bunch of them up there now, and even a helicopter. And they've come up with one astonishing scientific result after another. Amazing pictures like these. And one of the things that we infer from some of these pictures is that at some time in its history, water existed on Mars. This is an image from the Mars orbiter. And these rills here are believed to have been carved by liquid water sometime in the past. And here you have an idea of the scale here. So pretty high resolution. So this picture has resolution of a few meters. And so these channels here are believed to have been carved by water. So there does appear to be, even today, at least a small amount of liquid water on Mars, possibly locked up underneath the soil or underneath the ice caps. So that's very encouraging, because that already gives us 2 planets that have water. And in fact, there are more, which I'll show you in a minute. We also have some very controversial evidence of a sort from a particular meteorite. This is called the Murchison meteorite, more technically known as ALH 84001. It fell in Antarctica. And when they drill little slices off it and look at it under an electron microscope, they see this stuff at the top. Looks an awful lot like fossilized something, because at the bottom here is an electron micrograph of bacteria. Those things in the meteorite caused a huge uproar, because a lot of people believed, and some still believe, that those are fossilized bacteria that arrived from space. By and large, the scientific consensus today is that that is not what they are. It turns out there are geological processes that can create things that look a lot like that. And so most people are not, well, most people believe that it's not, in fact, fossilized bacteria. But the fact that it was even a possibility caused a tremendous amount of excitement. But there's lots of water elsewhere in the solar system. So here we have Earth. These are to scale. So here we have our own Earth on the right. And if you took all of the oceans and collected all that water into a sphere of water, this is how big the sphere would be. Water is very precious to us because there's actually not a lot of it. You know, I mean, the oceans cover the Earth, right? But it's a very thin layer. If the Earth were the size of a basketball, then the oceans would be about as deep as a coat of paint. So the biosphere, the area in which life can live on Earth, is a very, very thin onion skin around the Earth. And this is how much water we have on the whole planet. Europa is a moon of Jupiter. Europa has more water than Earth does. Titan is a moon of Saturn, the largest moon of Saturn. In fact, it's the largest moon in the solar system, and it has more water still. So here we have cases of moons around some of the gas giant planets, Jupiter and Saturn, that have more water than Earth, and not just water, liquid water. How can that possibly be? Jupiter is way outside the Goldilocks zone. If you were in orbit around Jupiter, you would be very, very cold. How can Europa and Titan have liquid water? And the answer is, oh, and here's another one, Enceladus. This is Saturn's moon, Enceladus. And look at that, spraying up from the surface of Enceladus. Those are geysers of water. Those are known to be water because we have sent space probes through them and collected samples of the molecules. So we have actual water geysers on the moon of Saturn. And the answer as to how one can have liquid water on a place that is... You muted me for a second there. All right. The answer as to how you can have liquid water on a place that is so cold is through the tides. Jupiter and Saturn are massive planets, and as their moons orbit them, the gravitational force, or I should say the differential in the gravitational force between one side of the moon and the other, stretches the moon, stretches the planetoid. That causes friction, that causes heating, and there is enough heating to melt ice. And because of this tidal heating, you have liquid water on moons of both Jupiter and Saturn. And that realization was quite an astonishing scientific discovery. So here's what it looks like if you cut Enceladus open. It's got a thick layer of ice. It's got some, well, I would call it volcanoes underneath. That's sort of what it is. It's got liquid magma underneath caused by the tidal heating that melts through the channel and causes these geysers on the surface. That's what the inside of one of the moons of Saturn looks like. Europa is one of the moons of Jupiter, and it's a similar story. You have a thick layer of ice, but underneath that ice, you have a huge ocean of water, which is kept in a liquid state by the flexion of the planet as it orbits Jupiter. This is considered a high scientific priority by NASA, and in fact, there is a spacecraft currently under development called the Europa Clipper, which is going to launch in 2 years. It's going to take 6 years to arrive at Jupiter, and it's going to orbit Europa, and it's going to send probes down, and it's going to try and get samples of that liquid water. It won't be really equipped to see life itself, but it certainly will go partway towards answering the question as to whether life could exist there. Well, so I've already named about a half a dozen places close to home that have liquid water. And that's really encouraging, because if there's liquid water in half a dozen places throughout our solar system, what does that mean for other planets in other star systems throughout the galaxy? Well, we want to explore that. And in order to explore that, first we have to find them. How do we find planets orbiting distant stars? And how do we search them for life if we do? Well, there's 4 ways to find planets. You could see it directly if the star is not too bright, or if you can block out the star. You can see the star shift slightly in position just from the momentum exchange as the planet orbits the star. You can see the velocity of the star, and I'll explain that in a minute, as the planet orbits around it. Or you can see light changes from the parent star if the planet passes in front of it, in between us and the star. And I'll show you what I mean by all 4 of these. The point being that there are 4 ways to find planets around other stars. So number 1, seeing it. This is an actual image of a star called V1032 Centauri, also called PDS 70. It is 370 light years from Earth. And this is an image taken by an array of radio telescopes, actually millimeter wavelength telescopes, in the Andes Mountains in Chile. And this is quite a remarkable image. This is quite recent, as a matter of fact. This particular one, I think, is only a few weeks old. So there's the star in the center. And this ring around it is a ring of dust that's left over from the formation of the star, and is basically the birthing room for planets to be formed. And right here, this little hot spot here, that is a planet about the size of Jupiter that has already been formed. And if you look carefully, you can see there's kind of a blob, a faint blob around that planet, and that is a moon being formed. So this is the first known instance, not only of a planet, well, we've had other instances of a planet, an extrasolar planet, being directly imaged, but this is the first known image of a moon being formed around an extraterrestrial planet. So this is an actual image of a planet orbiting a star 370 light years from Earth. So direct observation. So that's one planet. Having found that one and others that I will tell you about in a moment, a lot of people are all excited about finding more. And so there is a mission currently in the works. It's still in a very early stage. It hasn't gotten fully funded yet, called the New Worlds Observer. And what it is basically is a sunshade shaped like a flower petal. And then the satellite is parked behind the sunshade. And the sunshade is very carefully designed to look at some relatively nearby stars and block out the light from the star itself so that any planets orbiting would then become visible. Because otherwise, planets only shine by reflected light, just like Earth's moon and everything else in the solar system. And if the central star is too bright, then you can't see the planets because it gets lost in the glare, basically. And so this satellite is designed to block out the glare of the star so that you can actually see the planets. So that's another example of direct imaging, but that's still a ways off. I mentioned shifts in the position of the star. Star positions can be measured very, very accurately. And when planets orbit stars, the gravity of the planet, the star and the planet interact gravitationally. The planet attracts the star and the star attracts the planet. And so when the planet moves around the star, it causes the star to change position slightly. And we can measure this. So here's an example of a planet going around a star. Here. This is what it looks like if you're looking at it from above. See, the star appears to be wobbling a little bit, and we can measure the positions of stars very, very accurately. And by looking for cyclic position changes like that, we can infer the existence of planets. And this has been done actually quite a number of times. And these other stars are the reference stars. So that's a somewhat indirect way of measuring the existence of a planet through the position of the star. The third way is related to this because when the star moves, it causes its emission to shift. Every star emits a spectrum. If you look at a star through a prism, then you get all the beautiful colors of the rainbow, but you get some slots missing here. This will work with the sun, by the way. If you get a little prism and you hold it against the sun and project it on a sheet of paper, you can actually see this. These dark lines here are caused by absorption by atoms in the atmosphere of the star. And when the star moves, the velocity of the motion causes the wavelength of that line to shift. It's called a Doppler shift. It's exactly the same phenomenon that you hear when a siren passes you. As it approaches you, the pitch is high, and then when it passes you, the pitch drops. We've all heard it. An ambulance or a fire engine, as it passes you, the pitch drops. The same thing happens with light. We can measure the change in wavelength or frequency of these lines in the spectrum to infer the velocity of the star. So again, if you have a planet orbiting a star, then the spectrum of the star shifts. When it moves away from us, it's shifted towards the red. When it's moving towards us, it shifts towards the blue. And by looking at that spectrum of the star, we are measuring its velocity in much the same way we were measuring its position before. And that tells you, when you see this systematic back and forth in the motion of the star, that tells you that there's one or more planets there. And by analyzing it carefully, if there's multiple planets, you can decompose the whole thing and even infer how many planets there are and how much mass they have. So that's the third way. The fourth way is called a transit. And a transit happens when, if we happen to be lucky enough that the plane of the orbit of the planet is between us and the star, when the planet passes in front of the star, it blocks off a little bit of the starlight. So a planet like this, as it orbits around, doesn't change anything, but a planet like this, as it passes in front of the star, causes the light from the star to diminish a little bit, right? Stars are much bigger than planets. It doesn't block out very much of the light, but it does block out enough to measure. And this turns out to be an extremely powerful technique for finding planets. Whoops, sorry about that. We even have it here in our own solar system. This is the sun, our own sun. You can see the sunspots. And if you will watch for a moment, you will see the planet Mercury passing across the sun. Now, if you were measuring the brightness of the sun very carefully, you would see a very small drop in the brightness while Mercury was passing in front, because as you can see, it's shadowed, it's black, it's silhouetted. And so it's consequently, it's blocking off a very tiny portion of sunlight. Not enough to notice with the naked eye, of course, but we have instruments that can detect that. I'll let it get to the edge. And there we go. And that is called a transit of Mercury. And so we built a satellite to look at lots of stars to see if we could measure that. The satellite was called Kepler. It looked at a particular area of the sky that held 150,000 stars. It was launched in 2009. It operated for almost 10 years. And by using this transit method that I just described, by looking for small changes in brightness among these 150,000 stars, Kepler discovered 2,662 planets. 2,662, that's a pretty big increase in the number of planets that we know about. And if you do the statistics of it, knowing that it's only looking at a small fraction of the sky, and also knowing that this only works when the planet is in between you and the sun, you can derive how many planets there must be throughout the entire galaxy. And the answer turns out to be somewhere between 100 and 400 billion planets in the galaxy. There are between 100 and 400 billion planets in our galaxy orbiting many, many stars, which Kepler discovered 2,662. This is the area of the sky that Kepler looked at. It's only a small fraction of the sky. In fact, if you hold up, well, maybe a small dinner plate or both of your hands, if you hold up both of your hands at arm's length and kind of block off the sky, that's about how big this area of the sky is. So that's a pretty small fraction of the sky. It's roughly 100 square degrees. And it's based on the fact that it's only a small fraction of the sky, and based on the fact that it only works when the planet is in between you and the star, that's how you're able to do the statistics and come up with that 100 billion number. And this is what the data looks like. Right? We're looking at the star, we're looking at the star, we're looking at the star, and whoop, suddenly the star gets a little bit dimmer, and then there it is back at its normal brightness. I want you to look at the vertical scale here, right? It goes from the depth of the dip here is about 0.99994 compared to the normal brightness of 1. So you're looking at like 1,000th of a percent dip in the intensity of the star. That's how sensitive the instruments aboard Kepler are. And this is what the Kepler field looked like at about halfway through its mission. It was launched in 2009. 4 years later, it had already found many hundreds, I guess maybe even 1,000 planets, and this is how they were distributed all over the field of view. And you can see that they're pretty evenly distributed, which implies that they're pretty evenly distributed over the whole sky, which means the whole sky is full of planets. And based on the size of the dip, we can even estimate what the size of the planets are. And so the different colored dots correspond to different sized planets. And if you're looking for little pale blue ones, like here's a couple over here, those are planets that are about the size of the Earth. And then the pale green ones, of which there are very many, are ones that are maybe twice the size of the Earth. So you can see there's a whole lot of kind of Earth-sized planets out there, which is very exciting all by itself. The interesting thing is, as though there weren't any interesting things so far, is that based on the size of these planets and the distance from their stars, we can estimate which ones of them are in that Goldilocks zone, in that habitable zone where water, liquid water, has a realistic shot of existing. And this slide is actually several years old, but at that time we had already identified on the order of 20 planets in various star systems that potentially could have liquid water and then consequently be sufficiently similar to Earth that life could arise on them. That's a pretty exciting prospect. How can we pursue that further? How can we determine whether or not there is life on them? And the answer, you'll be happy to hear, is currently about 1 million miles from here. The James Webb Space Telescope, billions of dollars over budget, and about a decade late, finally launched, is performing just astonishingly well. Its first science results are going to be released on July 12th. So just about a month from now. And what is the James Webb Space Telescope going to tell us? Yes, let me say one more thing about it. The mirror is much larger than the Hubble mirror. The Hubble mirror is about 8 feet across. And the James Webb Telescope mirror is 21 feet across. It's very, very sensitive. And the Webb telescope is designed to be able to search for water. Unfortunately, this slide has a picture of the Hubble, but sue me. When starlight passes through the atmosphere of a planet, molecules in that atmosphere absorb certain wavelengths. And Webb can look for that. It's a spectrum, right? Just like molecules or atoms in the atmosphere of the sun cause those dark lines in the spectrum, same thing happens with planetary atmospheres. And the Webb telescope has enough sensitivity and resolution to actually look at the spectra of distant planetary atmospheres to see what molecules are in them. It can see water, and if it sees methane, methane is a very simple compound made out of carbon and hydrogen. It's 1 carbon atom and 4 hydrogen atoms. And the cool thing about methane is that not all, but many of the processes that make it are biological. And so if Webb sees the spectrum, the spectral signature of methane in a planet's atmosphere, that drives the odds way up that there's some kind of life going on the surface of that planet, or at least in the atmosphere of that planet. Ditto for water. The James Webb Space Telescope is designed to search for the spectrum of water, to look for candidate planets for life. So what will it find? Well, nobody knows, right? It may well find organic compounds such as methane, as I said, which is likely biological, although not certainly so. It may find water, and it may find all this on planets that would encourage us to look with a radio telescope to see if anybody is sending us one of those 23 by 79 grids. The bottom line is that our own oceans prove that life is tenacious and can exist well outside of the environment where we ourselves thrive. It is also the case that we are finding water and life-friendly energy sources in our own solar system in at least a half a dozen places. And thanks to Kepler and other programs, we are finding thousands of extrasolar planets, planets orbiting distant star systems, some of which are in the so-called Goldilocks zone where liquid water may exist and life could arise. These are very, very important and very exciting prospects. This is genuinely a golden age of astronomy, and the payoff may be the ultimate prize, the knowledge that life exists beyond our own world.